I'm a postdoc from IHEP in DC, and I am very glad to talk about the experiences of CPC detector and the integration status of the CPC to the ECTS. So the CPC, which is called as the circular electron position collider, aims to precisely measurement the Higgs particles and to search the new physics. And the ideal plan is that around this decade, we're trying to build the E collider, which CPC, and then in the next few decades, we're going to try to build the PP collider as PPC in the same tunnel. And the status of the CPC is we have already finished the CDR release in 2018, and now we're doing the TDR work. So let's come to the CPC tracking detectors. Actually, we have three design of the CPC inner tracker detectors. Here I just want to talk about the two design which we have already implemented in the ECTS framework. The first design, the baseline design, which is composed of the silicon detectors and the TPC. For the silicon detectors, it is I don't see much difficulties in implement geometries. While for the TPC detectors, it is very interested in ECTS, and there are already some nice talks to talk about the TPC problem. Well, I'm going to talk about the details in next few slides. And the second design of the CPC inner tracker is the full silicon design, and our aim is to going to support both designs with the ECTS tools. So this slide is talking about the status of the CPC ECTS integration. I would like to split into two parts. While for the framework integration, since the CPC frameworks is just have finished finished the migration from the Marlin framework to the Gaudi kernel framework, and we're going to try to integrate the ECTS to our new CPC framework, and probably will be a postdoc in next few months to do works about this. And for the detector study, currently our detect status all in the ECTS is under the ECTS framework. We build the detectors with the DD4HEP and build the geometry, do the material mapping, and test the examples existed in the ECTS framework. So for the baseline detector, we have the silicon detector and a simplified TPC with 220 sensitive surfaces, which is actually cylindrical surfaces surrounded by each other, which is related to the end cap readout, as Marcos have commented about it. And since currently we think that although it is not very looks like not very homogeneous, but the time spent on the extrapolation we can stand at the currently, because there's not too many tracks in the CPC event. So for the baseline detector, the geometries and the materials are validated with the examples supporting the ECTS framework. And for the full silicon detector, the geometry and materials is implemented, but it is under validating. Okay, so for the CPC tracker geometry building, we build the geometry with the DD4HEP. And here's some pictures about the double-sided pixel detectors in the DD4HEP view, the ECTS output OBG, and the ECTS sensitive surfaces in the navigation level. And for the TPC, we built the 220 sensitive tube surfaces, and it could be possible to change to some other implementation, which is described in the previous report. And let's see in the future. So here's a propagation example we run under the ACTS framework. The propagation example is very powerful too to debug the tracking geometry to tell if the geometry is correctly built. So as you can see, here's the navigation wheel and the sensitive wheel, and yeah, here in the here 220 TPC surfaces. So it is all black, but here is the 10-layer based TPC view. We can see it's actually cylindrical surfaces built surrounded each other. And the next slide is about the material mapping example. It's about the material mapping tool. It is a very powerful tool, as you can find it in the Corrigan's report. And we tested now only with silicon detectors, and we describe the materials in the DD4 help XML file and use the Gentino to recall the materials and to use the tools of VCTS to write out the materials and do the validations. But for the TPC volume material, we didn't try it yet, and I think we can try it to as it used in the Atlas colorimeter. Yeah, because we used to think to use some virtual surfaces to map the materials to the virtual surfaces of TPC, but it is not really homogeneous. So we would like to use TPC volume material mapping. We'll try to test it. And the right pictures about the validations between the Gentino recording material and the distribution and the material after this material distribution after material mapping tools. And it seems there are some places inconsistent. I think it is probably because of the boundaries surface mapping. Need to for the CEPC detector needs to do more study to learn the details. But I don't think it is quite a big problem. And we also tested the common filter example. We used the FATRAS to generate simulated heat and use the heat smearing and to do the heat smearing and then the common truth fitting. And for the DD4 HAP detector, there is no digitization model, but we have tried some method to jump the digitization model or include the digitization model in the DD4 HAP. But the last we choose to jump the digitization model because it is not. We didn't have the idea to describe the digitization in the TPC detector yet based on the 220 surfaces description. So here's a resolution of the local parameters. I think it is it kind of look nice, but actually I look at the PT resolution with this common fitting example, but I see the same issue in the S-Phoenix detectors, that there is a long tail of the PT resolution, but I don't find out the reason yet, so I didn't put it here. Okay. So that is what we've done in the using the ECTS tools to do the validations of our that is our CPC detector, and we hope to use it as a tracking algorithm and do something like a material study and layout optimization study. Let's come to the experience and discussions. So as a user and developer, it's a very good experience to touch and learn all tracking paths from ECTS. It really helped me a lot to study all of the tracking paths. And from the CEPC part, and we are glad to see there are increasing people who are interested in the CEPC detectors and the ECTS project, and who would like to do some contributions to the CEPC detector validations, and as well as the ACTS, as well as the contribution to the ACTS. But and here is still many works to do about the details, material description, and the layout learning and optimization, and specific detector model study, such as the digitalization, and then the framework integration to our new Gaudi kernel CPC framework. So several discussions from the CPC point of view. As I followed the Andy for a long time, I don't have many technical details problem, but I would like to raise some issues. First is the gas chamber. I wouldn't like to talk here because it is fully discussed in several reports before. And the second issue is how do we do with the low transverse momentum track, since CPC is precisely measurement experiment. The tracking efficiency is really important, and so for the CKF, it could be a problem that if we go to the low transverse momentum tracks, especially when the tracks when the track is multi-turn tracks. And then is the long vertex tracks, and currently we based on the CKS finder, which is based on the seed finding from the inner tracker. But if I guess if we have long vertex tracks or with the tracks with long impact parameters, these tracks will probably lose if we don't do the seed finder cut very carefully. So if it is possible to do something like in the atlas, we use some global method to find the seeds in the TRT, and then do the out to int extrapolator as we have implemented in the CTS extrapolation propagator tools, to get back the tracks from the long vertex, to get back the long vertex tracks. Yes, this is all my slides, and thank you very much.
Great, thanks, Jen. Questions or comments?
Well, I put as a comment, I put in the live notes action items to follow up. One is certainly, and this is not new to us, we know it, is we need to find a solution, a proper solution for Bell 2, S Phoenix, and CEPC for a TPC wire chamber setup. I think that would help already three groups quite substantially. So this probably we should spin out into a at least temporary subgroup, which we have done already, but we could enlarge this a little bit.
Okay. I had maybe one question about the low transverse momentum tracks. How low do you actually need to go for CPC? And in particular, what problems are you thinking about with the CKF? Is it simply you'll find too many, or is there some other issue?
Yes, yes. I think for the atlas, atlas tracking, the low transverse momentum, which with the transverse momentum, when the transverse momentum is under 400 MeV, which means the track is just going to do the become the multi-turn tracks, it will directly drop that tracks. But for the CPC detector, we want to keep these tracks. Yeah, so we would like to find out the multi-turn tracks.
Yeah, I think.
Okay, well, let me comment. So actually, in Atlas, we are actually able to go quite a bit lower in momentum. For example, we did a low PT min bias paper where we went down to 100 MeV with some small tuning to tracking. The reason that we don't do it in general for Atlas is really a timing consideration, just because there's so many tracks down at low PT. Andy, did you have more?
Yeah, I just wanted to say, technically from ACTS, we of course there's no cut on how low you can go. There is a loop protection in the propagation, which is by default on, that stops the propagator after a bit more than half of a loop, in order not to following up looping particles.
Yes, I remember that. So is it in the future possible to open that?
Absolutely.
Okay.
But I mean, I guess there is going to be a problem if one wants to use the CKF, because of the fact that at low momentum, the tracks are bend a lot, that you might be picking up very many hits and making it slow. This would be my worry. Yes. At low momentum, and this would be something we need to think about how to tackle.
Yes.
Okay. Any other questions? Okay. Thanks, Jim.